All right, Ozarka here. This is going to be a video on analyzing graphs. And if you haven't seen the last video, the one that was on functions, you are going to want to watch that because it's going to make this video a lot easier to understand. All right, this first objective says, giving the graph of a function, determine where the graph of the function is positive, negative, or zero. So you should be able to do that by the end of this video. The last video kind of helped with this as well, but this will cement it in a little bit more if you were confused in the last video. The second thing, given the graph of a function, determine intervals in which the graph is increasing, decreasing, or constant. So now you're actually just checking, is the graph going up or down as we go left to right? And if it's not going up or down, then it's constant. If it's going up, obviously it's increasing. If it's going down, it's decreasing. I'll show you some examples on that later. Third objective, given the graph of a function, determine the local maxima and minima. Okay, so now we're going to define what a local max and local min is, and then we're going to actually show what it looks like on a graph so that you can actually determine those yourself. And the last thing right here, determine if a graph has symmetry, and if it does have symmetry, what kind of symmetry does it have? All right, the next thing here, analyzing the graphs of functions. A common technique for determining information about a function is to draw conclusions from its graph. Best thing about graphs is it's literally graphical. We can look at it and kind of get an idea about what is going on with that graph. If you just kept it as a formula, it's not as easy to figure out what the graph actually looks like until you make it graphical. However, once you learn calculus, graphical techniques will probably become less popular. I wouldn't say less popular necessarily, but in calc you actually go for analyzing graphs in a lot more detail, a lot more analytically, where you don't even need to necessarily look at the graph. Before we begin, recall that the graph of a function passes the vertical line test. We went over this in the last video. Any vertical line crosses the graph of a function at most once. Otherwise, it's not a function. So we kind of talked about this before. If you have points that stack vertically, automatically it's not going to be a function if that happens. Important definitions. A function is increasing. Okay, so you're going to need to know what increasing means. On any interval where the greater x values give greater y values. So as x increases, is the y increasing? On such an interval, the graph moves upward to the right. We kind of talked about that before. Decreasing is the opposite. It's going to be moving down to the right. And the last thing was constant. That means it's not going up or down. That just means it's constant. It's constantly saying the same. As you put more x values in, you're just going to get the same y value each time. The next term that you need to understand is a local, or also called a relative maximum value. So it forms like a hilltop. So if you have something like this, that would be considered a local max. It happens at the hilltop. Compared to the things directly to the left of it and directly to the right of it, it is the greatest. So relative to what's around it, it's a relative max. A relative min is the opposite. It's more like a valley. So if you have a graph like this and it kind of dips down at the bottom, that is where the relative min or local minimum would be. The next definition that we're going to look at is if a function is even, that means if you plug in a negative x value, you are going to get the same exact value as if you just plugged in a positive x value. Plug in the opposite signs of the same input, so -1 and +1, -2 and +2, and you get the same value for that, then the function is considered even if it does it for all of the x values. It's odd is if you plug in a negative input, just like we did before, but you get a negative of the original. Okay, hopefully you see the symmetry kind of within these equations here, these formulas. One has a negative input and it's equal to the positive of the positive input. This one, it has a negative input, but it's a negative of that positive. So one's negative and one's positive. Hopefully you notice the difference between those so that you could figure out whether a function is even or odd. We're gonna do some example problems involving all this stuff to cement it a little bit more, but I just kind of wanted to show you the terms first. Make sure you write those down in your notes as they are important for you to know and understand how to use. All right, this next one right here, it says sketch the graph of g of x equals -x² + 1. Determine open intervals on which g is increasing and decreasing. Determine any local minima or maximum. All right, rather than sketching this just because it's a video, I'm just gonna do a screenshot of the actual graph really quick so we can actually just kind of look at it a little bit more. But you obviously can sketch it. It's a skill that you're gonna need to know how to do for the class. But just for the sake of the video and time, I'm just gonna do a screenshot. Okay, so I have a screenshot right there of the graph. It is important to understand too that it goes forever this way and forever that way. So it should have little arrowheads on there. It doesn't really matter so much for what we're doing here. But the first thing it's asking for is the sketch. Okay, I'm gonna count that as my sketch. And then it says determine the open intervals in which it's increasing and decreasing. So increasing means it's going up left to right. So you can see it's going up left to right up here until it starts to go down. So the first answer for the increasing, I'm just gonna write here, increasing, it's going to be -infinity all the way up to 0 for the increasing. The decreasing is gonna be what happens after the 0 right here, and it's going down forever that way. So it's gonna be from 0 to +infinity, it's gonna be decreasing. Then it says determine any local minima or maxima. In this case, it's going to be a max, because of right there, you can kind of see it's going from increasing to decreasing. It's a hilltop. So the local max, I'm just going to write the coordinate for it. It's at 0, 1. Okay, compared to what's around it, 1 would be the highest y value that's there. You can also just view it as the hilltop. So the next one, it says, show that f of x equals 2x squared plus the absolute value of x is an even function. What kind of symmetry would you expect its graph to display? All right, so we kind of went over this quickly, but the main thing you have to understand, if something's even, that means the following is true. If I plug in negative x for the f function, you're gonna get positive, like f of x out of it. So basically where you started. So what I'm gonna do here is I'm gonna figure out this value here and see if it's equal to this where I started, this thing up here, the f of x value. So to do that, I'm gonna write 2 parentheses negative x quantity squared plus the absolute value of negative x equals f of x. From here, negative x squared is just going to be positive x squared, because a negative times a negative is just going to be a positive. The absolute value of that negative x is going to be the same as just the absolute value of positive x. And is this actually equal to f of x? Well, you look up here, this is what f of x was equal to, and it is equal to this right here. So that means that it is, in fact, an even function, and I just showed it. That's why I put a little check mark there. I did show that it was an even function. What kind of symmetry would you expect the graph to display? So anytime it's an even function, the graph will always be symmetrical about the y-axis. So about the y-axis means it is symmetrical with the y-axis basically being the middle of it. So what I'm going to do is I'm going to graph this really quick and kind of show you what I'm talking about. But anytime it's an even function, it's always going to be symmetrical about the y-axis. All right, so here is the actual function right here, and you can see it is symmetrical about the y-axis right there. On either side, it's equal, and that's going to happen for every single even function. Okay, kind of a cool looking graph. All right, the next one, it says, show that h of x equals x to the third minus x is an odd function. Okay, so if you remember the formula for proving whether something is odd or not, if you plug in a negative x for the function, you're going to get a negative of the positive input. So it's h of negative x should equal negative h of x. Okay, so it's the opposite of what we just did. Before we plugged in a negative value and you got the exact same value. This time we're going to have the opposite signs essentially for this. So first thing we're going to do is figure out what h of negative x even is. It's going to be something like that, equals negative h of x. Okay, x to the third is x to the third. Negative x to the third is also negative x to the third. So you're going to have negative x to the third here. This one is going to become positive. And you will notice that it's exactly equal to what we started with the h of x, only the sign's flipped. So this one has a positive x to the third, this one's negative. This one is minus x, this one is plus x. So because all of the signs switch, that actually does show that it's an even function. So I'm gonna put a little check mark here that basically showed it. What kind of symmetry would you expect its graph to display? So anytime it's an odd function, the symmetry is always gonna be symmetrical about the origin. Okay, so it's not as easy as just looking at the y-axis. You have to kind of look at it as like almost it's rotational. I'm going to show you a screenshot of the graph just so it makes a little bit more sense. All right, so here is a screenshot of the graph so you can kind of see. If I were to rotate about the origin, you can kind of see that it would end up stacking up on top of itself. So here's the origin right here. If I moved this part over, if I just kind of turned it, you'd see that it would fit in nicely right over here. And that's the kind of symmetry that happens with odd functions. So they're symmetrical about the origin because you're basically turning it around that origin right there. All right, the last question, the graph of function f is shown below. Determine the domain and range of f. Determine the intervals in which f of x is greater than 0 and the intervals in which f of x is less than 0. Now, I actually did this in the last video. I'm just using the exact same problem. So that those first like 2-3 sentences there, I kind of already answered. So the main thing I'm going to focus on this one is actually those last 2 sentences there. Determine open intervals on which f is increasing and decreasing. Determine any local mins and maxes. What I recommend doing for this is always just finding the local mins and maxes first, because that's actually the cutoff from where it goes from increasing to decreasing or decreasing to increasing. And what I mean by that is you'll notice it's increasing all the way up to here, and there's your local max, and then it decreases all the way down to the local min, and then it increases again. So those are like those critical points that basically, where you're gonna see the differences between the increasing and decreasing. So I always recommend finding those local mins and maxes first. So let's see here. Let's just do the local minimum, this part right here. It's gonna be based on this point right here. Let's just say that's, I don't know, 1.75 or something like that for the x. It's kind of hard to just eyeball it. And then it looks around like to be -1 for the y value, around like right there, -1, probably a little bit lower than that, but that's okay, doesn't really matter. And that's the local minimum. The local maximum would be this thing right here. And let's just say it's at, I don't know, -2.5 3 or something like that, and then the y value is 2 on it. Okay. And then now that we have those x values, that 1.75 and that negative 2.3, we can figure out the increasing. It's increasing from negative 5 to this point right here, which is negative 2.3. So I'm going to say increasing from that. And then it's also increasing from this point right here, which is that 1.75. So from 1.75 to 5, it's going to be increasing. The decreasing is that spot in the middle. So basically from here to here, and we know those values already because we figured them out. It's just going to be negative 2.3 to about 1.75 for the decreasing. So that's a video about analyzing graphs. If you have any questions about anything in this video, let me know.